You ever ask an AI a question and just wonder what is actually happening in there? It honestly feels like magic, but it's not. Today, we are going on an incredible journey from the most advanced AI all the way down to the tiny spark of electricity that makes it all work. Let's start at the top with the so-called magic we see every day.
We see AI writing poetry, creating these unbelievable images, even writing computer code. And it forces us to ask the most fundamental question, right? How on earth can a machine actually think? Well, here's the spoiler alert right at the beginning. It doesn't. A computer isn't thinking, not in the way we do. It's just following a very, very long list of instructions. So our mission today is to trace those instructions all the way back to their source.
Okay, so let's start at the very top of this whole thing, with the most sophisticated tech we interact with, large language models, or LLMs. This is the magic we're going to take apart piece by piece. You know, at its heart, an LLM is really just a giant pattern-matching machine. That's it. It's been fed a huge portion of the internet, and it's learned one skill incredibly well, predicting what word or token should come next in a sentence. Everything it does, and I mean everything from answering your questions to writing a sonnet, it all comes from that one simple goal. It's aiming for what sounds right, what's plausible, not necessarily what's true, and that's a huge distinction. So that LLM is a piece of software. But what even is software? This is the first layer we need to peel back, and it reveals this massive language barrier between what we want to do and what the machine can actually understand.
And you can see that barrier right here. On the left, you've got a simple command in Python. It's clean, it's something a person can read and understand pretty easily. But on the right, that's what the computer's processor actually gets, a raw stream of ones and zeros. It's called machine code, and it is a completely different language.
So how do we bridge that gap? How do we get from our language to the machines? Well, we use a special program called a compiler. You can think of the compiler as a master translator. Its whole job is to take our human-friendly code, break it all down, figure out the most efficient way to run it, and then translate it into those perfect binary instructions the hardware can actually execute.
All right, this is where it gets really cool. We're diving deeper, past the software, and we've hit the hardware itself. We have arrived at the physical machine, what is essentially a rock that we have tricked into thinking. Let's find out how we pulled that off.
The heart of your computer is the central processing unit, the CPU. And you can think of it as this impossibly dense city made of billions and billions of tiny little electrical switches called transistors. Let's take a closer look at what they are.
The transistor is basically the atom of our entire digital universe. It's a microscopic switch with no moving parts, and it's made from silicon, which is really just purified sand. And that number from the last slide, it means we've made so many of these things that they are, by an absolutely massive margin, the most manufactured object in all of human history.
And here's the secret sauce, the connection. A transistor has two states. It can be on or it can be off, and that simple physical reality gives us a way to represent the two symbols of binary code, 1 and 0. The entire complex language of the machine is built right on top of this simple electrical difference.
Okay, so what can you do with just on and off? Well, by combining a few transistors, we can create something called a logic gate. This little guy here is an AND gate. As you can see from the table, it only outputs a 1, or turns on, if both of its inputs, A and B, are also 1. This is the very first, most basic step of computation. It's a tiny, perfect, reliable decision.
And here is the single most important point of this entire journey. Every piece of software you have ever used, every video game, every app, and yes, every single advanced AI, when you get right down to it, is nothing more than the result of trillions of these dead simple logic operations happening at a speed that is almost impossible to comprehend.
So we've hit the physical bottom, electricity flowing through logic gates. But believe it or not, there's one layer even deeper. And it's not physical at all. It's the pure, abstract idea of what computation even means.
Way before the first transistor was even a glimmer in someone's eye, mathematicians were thinking about algorithms, these step-by-step recipes for solving problems. Then, in 1936, a genius named Alan Turing came along. He wasn't trying to build a physical machine, he was trying to define the absolute limits of what a machine could ever be capable of doing.
He came up with this purely theoretical device,
A Turing machine. It's so simple. Imagine an infinitely long tape, a little head that can read and write symbols on that tape, and a small set of rules to follow, like if you see a 1, change it to a 0 and move 1 step to the left. That's it. It's the simplest possible model of a computer.
But here is the truly mind-blowing part. The Church-Turing thesis basically states that this simple, imaginary machine is powerful enough to compute anything that is computable. Every real-world computer ever built, from the room-sized ENIAC to the phone in your pocket, is just a physical, really fast version of this one beautiful, abstract idea from 1936.
Okay, we've reached the absolute foundation. Now, let's quickly climb back up the ladder and see how this all stacks together to create that magic we started with.
The whole journey is a stack. At the very bottom, you have Turing's abstract idea of computation. That idea is made real by the physics of the transistor. Billions of those transistors are arranged into hardware, like a CPU. That hardware is useless until it's given software written by humans. And at the very top of the stack, that software gives us the applications we use every day, like AI.
So you see, the big takeaway is this. The magic isn't in any one of these layers. It's an emergent property. It's what happens when you stack layer after layer of simple, understandable ideas, and then you execute them at a scale and speed that is just completely beyond human comprehension.
Understanding this stack is, well, it's pretty empowering. It completely demystifies technology. It also reveals one of the most profound principles in the universe. Incredibly simple rules can generate almost infinite complexity. This stack, this is the blueprint for our entire modern digital world.
And all of this leaves us with one final fascinating question. For almost a century, we've been building this incredible tower, adding layer upon layer of abstraction. Now that we have things like AI sitting at the top, what comes next? What will we build on top of that?